My teammate sounds like a duck.
Sally, put it in your pocket.
There's just stuff like that in the water. No, that's it. That's bottom. Then we turn it upside down. Don't split it. They don't turn it upside down. They don't. No, they don't. Keep them right. Da da da.
Yes, like that.
Da da da. Da da da. Ronan. Nico. I don't know how she does it. The water disappeared. Dun, dun, dun. What happened? It evaporated. It can't evaporate that fast. No. It did. See, put glue into it. No, it's kind of like, I love this. That's the same trick. What did you pour in that? Baby powder. Baby powder. Baby powder. Baby Homemade baby powder. And then water.
All right, can we get another round of applause for Jamie? All right. So what Jamie just demonstrated was a unique property of sodium polyacrylate, which is used in diapers and absorbs an incredible amount of water. What's really cool about that stuff is if you take it and it's already in the gel form, it's absorbed the water. If you add a salt to it, the salt will suck the water out of the gel, and it'll turn back into the powder that you saw her pour on. Even more neat is, think about what that means with your diaper and a baby, right? Because urine has a lot of salts in it, which means they actually can't just use straight polyacrylate gel. They have to add more things to it so that it eliminates that property. Now, we're going to go over a number of reactions tonight. All of them involve change. Now, you know how you take your Legos and you can build things with the Legos and you take it apart and then you build something else with the Legos? Well, that's all that chemists do. They take molecules, which are made up of atoms, they recombine them in different ways, they take them apart, and they build them back up into different forms. And so we're going to largely be doing that today, along with a few phase changes, where you go from one type of matter into another, from a solid to a gas, for instance. But first we're going to start out by trying to put out a candle with gas. Okay? Now, standard
A visible gas.
standard tea light. And what do you think is going to happen if we take this cup and pour it out over the light? What do you think is going to happen? Think it's going to go out?
Nope.
Think it's going to go whoosh?
Gas. No, I think it's gonna go. It's gas. No, it's not. Not gas.
Nope. It's going to stay put. Now, that's because what gas is in here?
Air.
Air, that's right. But what if we actually add a different gas? What if we add a gas that will take away the oxygen and start the flame? So, Kara, would you like to?
Sure. So what we have here is some baking soda, which is sodium bicarbonate, and some vinegar, which is acetic acid. Have you guys all dealt with this stuff at home? Maybe baking cookies or something? Yeah? Okay. So what we want to do is just mix these two things together to form a reaction that makes carbon dioxide. And then we're going to try to pour it into our cup, which is over here, our empty cup, and then try to put out this light.
Same
Okay,
empty cup.
so again, same empty cup, nothing happens when you pour it on. So what I'm going to do, also watch carefully because we're going to ask for 4 volunteers or 5 volunteers after this to do the experiment. So watch us do it first and then you guys can do it yourselves. Okay, so on the count of 3, I'm going to pour it in. Ready? 1, 2, 3. So there are some bubbles. What do you guys think are in those bubbles?
Gas.
Gas? What kind of gas do you think it might be?
Carbon dioxide.
Carbon dioxide? Possibly. Okay, so these bubbles are now popping and the gas is sticking into the bottom of the cup because it's heavier than air. So I'm just going to pretend to pour the water, but I'm actually pouring the gas. So it looks like a pretend tea party. Front row, is there any water in here?
No.
Okay, so now I'm going to try to put out the candle.
That was gas.
Good.
Can we get 5 on? Okay.
Did you guys try pouring the empty cup on the glass on the table?
Okay, that should be good. And then, what do you think is going to happen? Oh, here, use this one.
Get me the water. You might want to pour a little bit more of the gas.
Yep, do it quick. Whoa! Good job. All right, excellent job, everybody. That was a volunteer. So we just used a solid and liquid, combined them to form a gas, and then used that gas to put out a fire. Pretty cool. Now, I don't know. Are you getting hot in here, Kara?
Ooh, it's pretty hot in here. I could really use some water.
Yeah, me too.
I have some water right here.
Okay, well let me get us some glasses.
Oh, that looks awesome.
But you know, we only have water, don't we? Because I could really go for some juice
Ooh,
too.
juice sounds really good right now.
All right.
Well, here's some water.
Oh, thank you very much. Oh, fantastic. Oh, we're running out of water.
Yep.
All right. Now, okay, I'm going to ask my magic cup to give me some like grapefruit juice.
Ooh, grapefruit juice. I'm going to ask for some strawberry juice.
Ah, okay, that sounds good to me. Okay, you guys think that we can get water and turn it into juice?
Yeah.
You think? Okay, on the count of 3. 1, 2, 3. Wow.
That looks like some really good strawberry juice, and that looks like some really great grapefruit.
Okay, would you like a
Oh,
straw?
that's always
I always take my juice with a straw. All right.
This is good. Dr. Matt, are you blowing into your juice again? I know, like, at least my mom told me not to do that when I was younger because the Magic Cup doesn't like that and it gets everywhere. And I think the Magic Cup is going to make it turn into water.
It is.
Look at that! Wow, that was so bad.
What? Why would you do that to me? I wanted juice. Okay. Well, actually, what we did here, do you think the glass is really magic?
No, we knew we couldn't trick you guys.
Yeah. Oh, we got to back up
Oh
behind the
yeah,
line,
blue
though,
line,
please.
guys, blue line.
So what we've done here is we've used a pH indicator called phenolphthalein, which in the presence of a base turns a different color. In this case, this kind of light violet. And what's neat about an indicator is that means if the pH is above a certain threshold, it'll be that color, and if it's not, then it'll slowly, the color will get lighter and lighter until it's clear. So for instance, we can take the cup, which is now clear, and it's clear because when you blow water or blow air into the liquid, you're actually making it, you're removing the basicity, turning it back into neutral. And we can make it basic simply by adding another base and turn it back into juice. Yes?
Is it actually drinkable?
I wouldn't. The base isn't going to hurt you. The phenolphthalein is in such low concentrations it probably won't either, but I wouldn't recommend it.
I think regular juice would probably
Regular
taste
juice is
better.
going to taste a lot better. But yeah, so we turned water to juice and then back into water through the use of a pH indicator, which is kind of cool. Now, who here would like to see some liquid nitrogen next? All right, so shall we set the mood then? All right, now liquid nitrogen is extremely cold, and nitrogen is in the atmosphere all around us all the time. What they do at an industrial scale is they take air and they separate it into its component gases, which are then liquefied. And liquid nitrogen is extremely cold, okay? So I need everybody to stay behind the blue line. That's just added on top of a little bit of water. It's just boiling off.
So, who thinks that they can break a penny? Does anyone think they can break this penny? You want to try?
Yeah.
All right, pass it around. Everyone try to break it. Pretty hard, huh?
It's really hard.
Pretty hard. All right, so the front row is still trying to break the
Back up,
penny.
back up, back up.
Yeah, make sure you stay behind the blue line.
Okay. Now, has anybody been able to actually break the penny?
No.
No?
Not successful.
Okay, now we've just taken some standard pennies and we had them in the liquid nitrogen between shows. Now, do you think Kara will be able to break the penny?
Yes. Yeah, I hope you will. Hammer, yeah.
Well, we could try a hammer on the other ones
Yeah, do
too.
you want to try it on the other one first?
No. Yes.
All right.
Yeah.
This not gonna work. Let's try this one. Does not break. Let's see if this one does. Broken penny!
That means I'm waiting for
Maybe it was just that penny. Should we try another
I
one?
think we should try another one.
No,
because
I think we
science
shouldn't.
replicate.
I think we shouldn't.
Broken penny again.
That was just make sense. That's what we're doing.
All right. He does the experiment. Okay, now standard balloon. I'm going to feed it here to the liquid nitrogen that we have in this vat.
This vat hasn't eaten in days, so it's really hungry for
Maybe we
balloons.
should get another one too.
Oh yeah.
Sit down,
Maybe
bug.
one of these
Sit
animals.
down, bug.
Sit down.
Sit down, bug.
Please.
Sit.
All right, now one of the neat things here, when I pull this out, look carefully. At the bottom, you're going to see a liquid. That's actually liquefied air. so cold it liquefied the air, separated it out, and then of course the thing heats out. I think it forms a last experiment, let's say you're out. Okay, let's say that you're out with your elephant family friends and boom, it's nighttime and they have to brush their teeth, but they forgot their toothpaste.
I love this.
And so, what do you say? Should we try to make some toothpaste for our elephant friends?
Yeah.
Alright, so let's start with the baby, shall we? Let's make some, oh, and actually I realized we have yeah, we're going to skip the baby. We're going to go to the adults.
Yeah.
Because for a lack of preparation. All right. So let's make some elephant toothpaste for the adults, shall we? This is a kind of cool reaction. What we're doing here is we're going to take concentrated hydrogen peroxide and we're going to convert it into oxygen gas. And we're going to trap the oxygen gas in a series of bubbles, okay, which is caught by a detergent. And it forms of what's called a very exothermic reaction, which means it gives off heat. So we're going to start with about 100 milliliters of concentrated hydrogen peroxide. We're good.
Okay. And what color should we make their toothpaste? We have red,
Yellow.
yellow,
Red.
yellow.
Blue. Red and blue. Can you mix red and blue?
Purple.
Add some blue to it. Red and yellow. Red, blue, and yellow. Red and yellow or blue?
Yeah, blue stripes.
Okay, we're going to try for blue stripes.
Last show of the evening. Got to really hit the bling.
Can we do yellow with it?
Alright. That's enough.
Okay, add a little bit of detergent. Stir it up. And here, you want to do the honors?
Sure. Gotta put on my safety glasses. Okay. Okay, can I get a countdown from 3, 2, 1.
Oh my.
But let's try again. Okay, so we're going to take this can, or this match, blow it out, stick it in here, and hopefully... Well, yeah, it's hard to see. It's really hard to see. So, it actually, there's enough oxygen in the foam after we let it go that it will catch the light. It'll turn the embers in the match back into a flame, as you can pull it out and the flame's back on, but it's awfully hard to see. So we'll skip that part. But yeah, last show of the evening. I hope you guys had a good time. Learned something.